Hello to everybody and welcome to this tutorial. In this tutorial I would like to show you how to do topology optimization with Abaqus. What is topology optimization? Well, it's the process in which we can get a reduced volume component from its original shape. Topology optimization can be divided up into 4 stages. We start from an original design and the final element software give us the topology solution. We need to make sure that this topology solution can be manufactured, getting a refined design that we need to verify at the end. So in this video, we are going to learn how to get this topology solution with Abaqus. To do so, we are going to use a Flange model like the ones shown in the following pictures. So we are going to define the exercise. In Abaqus, we are going to create a 2D Flange model, very simple one. It's just a surface with several holes, and it's going to have a distributed load on the top edge. The material is going to be steel, and the target of this optimized topology optimization is going to be an optimized geometry, just as I said before. How? In this particular case, we are going to try to minimize the strain energy by reducing the volume more than 30%. And the Abaqus units will be newtons, millimeters, tons, and seconds. In this exercise, what we are going to do is just create a general rule for a general Flange model. So if you need more precise geometry, topology optimized geometry, you need to import your full Flange model, okay? Also in this case, you need to notice that we are going to freeze all the top edge as the load is going to be applied there. So we are going to get some modifications in the structure here. So what I mean is just this model is going to be for internal Flange models, like in this one. If you would like to do an external Flange connection, you need to apply your load in the internal side, okay? So in this particular case, we are going to apply the load here, in this case. This is going to simulate a centrifugal force, which is the one that this example gas turbine voltage Flange is going to suffer. Okay, so we can start our model with Abaqus. First of all, you need to make sure that you set your work directory. So in our case, it's okay. So first of all, we need to import our part. So in this case, it's already imported, okay? But you need to make sure it's okay. So the next point is going to be define our material. Material is going to be steel with elastic properties, Young modulus, okay, 0.3, I think it is, yeah. Next thing will be create section. Section is going to be a shell, homogeneous, made of steel and 10 millimeters thickness. And last, we are going to create property. Okay, so we are going to use the section created before. Okay, so next thing will be create the assembly. Flange, okay. So yeah, we need to go to assembly, select Flange and click in make independent. So one thing we need to know is create a partition. In our case will be the holes. This partition will help us freezing the parts we don't want to modify. We don't want the topology optimization process to modify. Okay, so we're going to create from a sketch. Okay. So we are going to sketch all these holes we want to partition. Okay, so it's done. Okay, looks good. So next step is just create a step load. Okay, static one. Okay, maybe we can decrease the increment size, initial increment size. Okay, load. So going to load, we need to create two different datums. This is going to help us defining the boundary condition. As we are going to use 1/4 of the Flange model, the boundary condition definition will help us to define the cyclic symmetry. So the boundary condition will be to restrict all the normal movements, displacements, normal to this x to the x in this case the x axis. Okay, so this motion applied to this plane will be restricted. Okay, so first datum is created, so we need to create another one. Okay, created. So now we can define the boundary condition. Displacement rotation. We need to select the regions. Will be all this edge. Need to remove the y displacements. So yeah. Also, as this is 2D, we need to remove the z. This z motion. Okay, sorry, I forgot to apply the local datum. So we need to, okay, now it's done. Okay, so we need to do exactly the same at the opposite end. Okay. Okay, so we need to apply the load. Load is gonna be a shell edge load. That will be 100 megapascals. Wow, yeah. Okay, so next step will be to create the mesh. to check the mesh. The elements will be standard, yeah, S4R, that's great. So mesh controls, we select quads. Global seeds will be, this will define the global element size. I want 2 millimeters. And last, we create the mesh. Okay. So now we set the model to start the topology optimization. First, we need to run this model as it is. Okay, so we go to job, create a job from this model, Flange model. Okay, submit. Shouldn't take too long. Okay, so the model is completed, the run is completed, so we can check the results. So you can check the deformations and bone misses stress. Everything looks like everything makes sense. Oops, we can animate. Yeah, you can see how boundary condition is well defined. So the model looks good to me. So yeah, the model is run. So we have everything now to define the topology optimization. So next we need to go to optimization and we need to create an optimization task. So yeah, and here we need to select the region. Okay, so as I said before, we need to freeze load regions. We would freeze boundary conditions, although we are not going to do it. We can leave everything as default. So next we need to create our variables. Variables will be design responses. In this case, strain energy first, apply to the whole model. Okay, and the next one will be the volume. Apply to our region. Okay, so next thing will be create an objective. The objective will be the function we need to minimize. So we need to minimize design response value of the strain energy. Okay, and next we need to define the constraints. Constraint will be the volume. So in this case we need to put 0.6. This is we are going to freeze the 60% of the region of the volume, as we said at the beginning. Yep, the volume, reducing the volume more than 30%. So we need to constrain 60% of the model. Okay, so the next thing we need to do is just go to job. Okay, so we need to go to optimization process manager. So we're going to delete this one. It's just a test. Here we need to select the task we created in optimization process, optimization module. 50 cycles. Select specify cycles every 2 cycles, every 10 cycles, sorry. Submit. Okay, this can take a while. This is going to be an iteration process, like a trial and error, following internal algorithms. So I'm going to pause the video, show you the results later. So the run is completed. So here we have the monitor, can plot all the iterations and see how the objective function is reduced, the string energy is reduced every cycle. So okay, so we need to check the result, the final shape from topology optimization. We need to combine all the results. Okay, submit. Okay, close. Go to the results. Okay, so the optimized component Abaqus show us should be this way, with these holes inside the Flange model. So we can go and see material properties normalized. So this graph indicates where the material is more needed. So red parts, the material is totally necessary. So if we go to cut view, yeah, you can see how the whole component indicating where the topology shape is. So yeah, this is the result. With this, it's obvious with this topology optimization tool we can save a lot of weight, very important for several components in aerospace industry, oil industry, automotive industry. It's very useful. So that's all. Thank you very much for watching this video. Please subscribe to the channel and like us. See you later.